section 6.3, volumes by cylindrical shells. In this section, we're going to learn another method for finding the volume of three-dimensional shapes that are created when rotating an area around an axis. So to see why we need another method, let's consider the region under the curve y equal 2x squared minus x cubed and between x equals 0 and x equal 2. And let's take that region and rotate that area about the y-axis. So first of all, just as a little sketch to see what this might look like, this region is in the first quadrant, so between x equals 0 and x equal 2. And if you were to sketch this, it would look a little bit something like that. And now we're going to take that area and we're rotating it about the y-axis. So when we do that, we're essentially creating this three-dimensional shape. And you can kind of imagine it's sort of like those cone shapes that maybe we saw in the previous section. It's got a hollow center almost. It does actually have a complete bottom there, so it isn't hollow at the very bottom of the shape. So, I don't know, again, going back to food contemplations with these shapes, maybe this is a pet food bowl. There you go. So your dog is eating out of this bowl, and you're trying to figure out what is the volume of this three-dimensional shape. So if we were to try to do this using methods that we saw in the previous section, we would have to use discs or washers. And it would essentially be a washer all the way until the very bottom. But the washer method wouldn't really work because you would have to figure out what is the inner radius, which is essentially the distance from the axis of rotation to like the left-hand side of this blue curve that I've drawn for the area. And then you'd also have to figure out what is the outer radius, which would be going from the axis of rotation to the right side. And so a couple of problems occur. First of all, you'd have to find a place to split where you're determining what is the inner radius from the outer radius. It's all dependent on that one curve. And then also, if you actually wanted to get an expression for the inner and outer radius, you would have to take that equation and solve for x in terms of y, which means getting x by itself, which is actually not a very easy thing to do. Solving a cubic equation to just get x by itself and everything else on the other side of the equal sign is in terms of y, that is not easy. So because that is not easy, we would like another method to find this volume. The cylindrical shells method is an easier method of doing that than the washer method for this particular shape. So let's see what that method looks like. So now instead of cutting this horizontally, remember if we're using the washer method, we are slicing perpendicular to the axis of rotation. Imagine cutting that shape into cylinders. So what that means is I'm going to imagine that we can cut this shape and we can create cylindrical shapes. But these are going to be somewhat hollow inside. And then imagine that you can create more of those and stack them one inside the other. So each one of those is going to be called a cylindrical shell. If we look at one shell, it has an inner radius and an outer radius. So thinking of the one that I have in black here, just drawing it a little bit larger, if I've got a shell, then I have an inner radius, which would be from the center of the shell to where the shell actually starts. That would be an inner radius. And then an outer radius where it starts from the center of the shell and goes all the way to the outer edge. So it has an inner radius and an outer radius. The volume of this shape that I've drawn here is found by using this. Here I've written volume equals pi times r2 squared times h minus pi times r1 squared times h. h is just the height of this cylinder. R2 would be the larger radius. R1 would be the smaller radius, or inner radius. And all you're doing with this subtraction is taking the volume of the larger cylinder and then cutting out the volume of the inner cylinder. And what you're left with is just a shell. So I'm taking two volumes and subtracting them. This is exactly like finding the areas between two curves. We're using subtraction to find what's left. So here there's a common factor of pi and also a common factor of h. So I've written pi out at the front and h out at the end. And then I would have r2 squared minus r1 squared, which is a difference of squares, and I can factor that and be left with r2 plus r1 times r2 minus r1. So now I'm going to manipulate this a little bit more. I'm going to introduce a factor of 2 out front, but I have to compensate for that by also dividing by 2 in this fraction. So I'm really just introducing 2 over 2, but then separating it this way. And then instead of writing r2 minus r1, which is the difference of two numbers, I can represent that as a change in r. So I'm going to replace r2 minus r1 with delta r. And then finally, the fraction that's there, r2 plus r1 divided by 2, that is really just the average of the two radii. So I can just write that as a representative radius. How about we just call that r? R is representing the average of those two radii. So thus the volume for one cylindrical shell is volume equal 2 pi r, which we can actually recognize as the circumference, times h, which is the height, and then times delta r, which is the thickness of a shell, reusing that word thickness that we saw in the previous section. So the thickness would just be how thick is it from the inside to the outside of the shell. And you've seen these sort of shells all the time. If you imagine a paper towel roll, when you're done with all the paper towels, there's the cardboard roll in the very center. There is a thickness to that. If there wasn't a thickness, then it wouldn't exist. So it's a small thickness, but it's there. So imagine this is the same idea as that. So if we have a solid capital S that is obtained by rotating f of x about the y-axis, like we have up here, for a less than or equal to x less than or equal to b, then we can divide the interval from a to b into n subintervals of equal width delta x. Using the midpoint of each interval, we can get the height of a cylindrical shell with average radius x sub I bar. Anytime you see a bar over a letter, that is usually standing for average or mean or midpoint. The height is the function evaluated at that midpoint, and the thickness is delta x. So just replacing the use of r now with x bar, we get that the volume is equal to, just for one shell, 2 pi x sub I bar times f of x sub I bar times delta x. So now let's add n of those such shells and then let n go to infinity, and we get a definite integral, giving us the volume is equal to the limit as n goes to infinity of the sum from I equal 1 to n of 2 pi x sub I bar f of x sub I bar delta x, which we also know as a definite integral, the integral from a to b of 2 pi x f of x dx, where, and this is important, a is between 0 and b. So you're considering here the limits of integration for this general definition would be positive. But things can obviously change, as we saw in the previous section. So what I want to point out from this definition, we are going to be using this integral, but I want to point out that the x in the integrand is the radius. So it might be helpful if you keep that in mind. This x is not always going to be just the letter x, but it is going to be the radius. And f of x is the height of the cylinder. So if we start seeing examples where we rotate about an axis other than the y-axis, the radius will not stay as the letter x. We're going to have other representations, just like we saw in the previous section. And also, if two functions are used to make the height of a cylinder, then f of x may actually be the difference of two functions, like we saw in section 6.1. So we're going to see some of the ideas of subtraction that I was using in the previous section to find out what radius and height are in later examples. So before we see some more complicated examples, let's actually calculate this volume that we were talking about to begin with, just using our simple definition that we ended up with. So example, find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equal 2x squared minus x cubed, and y equals 0. And again, I want to redraw this so we can see what are these cylindrical shells. So again, just a little sketch of what this looked like. This is x equal 2 there. Notice in this example, it just says bounded by y equal 2x squared minus x cubed and y equals 0. That is this shape here. And so the limits of integration are just going to be x is between 0 and 2. And then what a cylindrical shell would look like, I'm just going to imagine this red line represents the thickness of the shell. The fact that you can see the red line means that it has a thickness. But we can imagine that if we're thinking about limits heading towards infinity, this can be infinitely small but still have a thickness to it. This is occurring at some value x that's between 0 and 2. So now if I take that red line and I rotate it about the y-axis, this is where you get that cylindrical shape. So now here's some things that we can point out with that. That red line is representing a height. And to get us used to what we'll see in later examples, that height is really just how far is it from the top here to the bottom. If your height is a vertical distance, that has to be the difference of two y values. So just like I did in the previous section, this height is the dot at the top comes from y equal 2x squared minus x cubed. And then the dot at the bottom comes from y equals 0. So really my height is 2x squared minus x cubed, that's the top function, minus 0. So it's just 2x squared minus x cubed. The radius, that comes from, you put down some marker on the axis here of x. This is a value between 0 and 2. But that is a certain distance from the axis of rotation. So the radius, notice this is a horizontal distance, so it has to be an x value minus another x value. And this is going to seem overly complicated because our radius is just going to be x, but I'm setting up a pattern that we can then use for the following two examples where things get a little bit more complicated when your axis of rotation changes. But I'm still using the concept of subtraction. My radius is the x value on the right, which is really just x, minus the x value on the left, which, what's the x value at the origin? It's 0. So really this just turns into x minus 0, or just plain old x. So all I'm pointing out here is we're still getting the same x that was in the definition and the same function, but I'm setting up the subtraction pattern so that when things change, you'll see that those same concepts of subtraction work later on. So this is verifying that our definition was correct. So now, my volume is just the integral from 0 to 2 of 2 pi times my radius times my height, which is 2x squared minus x cubed, and then I'm integrating with respect to x. All right, so I just replaced everything in my definition, and now all that's left is just integration. I'm going to factor out my constant 2 pi. If I have x times a polynomial, I should actually distribute that. We don't want to use the substitution method. That would be overly complicated. But distributing the x to 2x squared minus x cubed gives me 2x cubed minus x to the fourth dx. Antiderivative of 2x cubed would be 2x to the fourth over 4 minus x to the fourth antiderivative would be x to the fifth over 5. And while I'm here, I'm just going to divide the 2 by 2 and the 4 by 2. And then I need to evaluate at 2 first and then 0 second. So this gives me 2 pi times the quantity, first plugging in 2. I would have 2 to the fourth divided by 2, so that's 2 to the third or 8, and then minus 2 to the fifth, which is 32, divided by 5, and then plugging in 0, I would have 0 minus 0. So then I end up with 2 pi times 8 is the same thing as 40 over 5. So then subtracting 32 over 5 leaves me with 8 over 5. And so then I just end up with 16 pi over 5. Okay, so now let's take a look at another example where the axis of rotation has changed. And I'm taking this from the homework. This is just a setup question, and it would be multiple choice. You'd have options to pick from. So we're just going to set this up. Define capital R as the region bounded by the graphs f of x equal 2 square root of x and g of x equal to x squared over 2 in the interval from 0 to 1. Which of the following represents the volume of the solid of revolution formed by rotating R about the line x equal 3? So one thing to point out, our axis of rotation is changed. Our axis of rotation in the previous example was the y-axis, which remember that does have an equation, x equals 0. So now we've changed our axis of rotation to x equals 3. So first thing I'm going to do is just do a little sketch just to see what I have here. So first f of x is equal to 2 times the square root of x. So I need to plug in some positive numbers into this. I'm going to go up to 4. If I plug in 0 to f of x, I just get 0 out. If I plug in 1 to f of x, then I get 2 times the square root of 1, so that's 2. So I have a coordinate at 1, 2. And then if I plug in 4 into f of x, I get 2 times the square root of 4, so that's 2 times 2, or 4. So now I have some points for f of x, and I can draw a curve representing those. And then g of x is x squared over 2. And again, I'm just going to plug in a couple of numbers. So when x is equal to 0, I get 0 out for g of x. When x is equal to, I'm going to skip over to 2. Plugging in 2 into g of x, I get 2 squared, which is 4, divided by 2. That gives me 2 back out. And then if I plugged in 3, I would get 3 squared, which is 9, divided by 2 is 4.5. So I would get some curve like this. And there's g of x. Now we're not looking at the whole enclosed shape there because they've only restricted from 0 to 1. So what you can imagine is that it's like I'm just cutting this region and I'm looking at this particular area. So I'm taking that area that I've shaded in red and I'm going to rotate that about the axis of rotation. The axis of rotation is here at x equal 3. So what you can imagine is I'm just going to take that shape and rotate it about that line x equal 3. And I'm going to use cylindrical shells for this. The way that I'm going to do that is just draw a vertical line that's parallel to the axis of rotation. So one thing to keep in mind is the height of your shell is parallel to the axis of rotation. So the height is parallel to the axis of rotation. So now let's use the ideas of subtraction that I saw in the previous example to see how we could find the height here. So if this black line is representing the height, notice that the top comes from f of x and the bottom comes from g of x. So the height is really just f of x minus g of x. See how that theme from section 6.1 keeps coming back, this idea of subtraction. F of x is the function 2 squared of x. And g of x is the function x squared over 2. So here, the height comes from the difference of two functions. That's what I was pointing out earlier. And then my radius, where I've drawn this black line, that has a corresponding x value that, notice, is in between 0 and 1, which was the limits that they gave us for the interval. Now, how far is that x value from the axis of rotation? How would I find the radius is what this is talking about. Exact same concepts that we saw in the previous section. The radius is also going to use subtraction. And remember, we use greater minus lesser. So when you're comparing the x value that's between 0 and 1 and the axis of rotation, which is x equals 3, 3 is always going to be greater than whatever number is between 0 and 1. So there's only one way to find the radius here. It's taking the greater number, which is 3, minus the lesser number, which is some value x between 0 and 1. So keep this in mind with height and radius. We're using subtraction, and it's either top minus bottom or right minus left. That's an easy way to approach all of these. Okay, so then my volume is the integral from a to b. Those are my limits of integration, times 2 pi times the radius times the height. And then integrating with respect to our independent variable. And if your height and radius are in terms of x, that's giving you a clue that you are going to be integrating with respect to x. So then my limits are from 0 to 1. My radius is 3 minus x. My height is 2 squared of x minus x squared over 2. And then dx is my differential. So this would be the answer in the homework problem where you're just asked to set it up. How would you solve this? Exactly like I did the previous one. Factor out the 2 pi, multiply everything out in the integrand, and then you're really just going to be using the power rule for the antiderivative. So now one more example, but now we are looking at, instead of a vertical axis of rotation, a horizontal axis of rotation. So in this example, use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. So note now the axis is horizontal. The last two examples had vertical axes. And also remember, in the last two examples, the height of the shell was parallel to the axis of rotation. So we have to have the same thing here. So this time around, the height, quote unquote, will be a horizontal distance. So let's see what that means. So first of all, I'm looking at the curve y equals square root of x from x equals 0 to x equals 1. So that's just going to have a point at 0, 0, and then another point at 1, 1. So there's our function, y equals square root of x. Now we are rotating about the x-axis. So that's our horizontal axis. So if you think about what this would look like, like a parabolic dish, essentially. You can kind of see where this gets applied in other areas by just thinking of simple two-dimensional functions, but then rotating them, and you get three-dimensional shapes that we're actually pretty familiar with. So we could actually solve this using the washer method, or actually more specifically the disk method, because this wouldn't have a hollow center. So you could slice this with vertical slices that are perpendicular to the axis of rotation, and you could find the volume. So do that on your own to check against what we're about to do. What we're going to do, though, is use shells, which means that I'm going to have a height that is parallel to my axis of rotation, which has to be something like I've drawn there in red. There's a stopping point on the right. X doesn't go any further than 1. So this red line goes between the curve and the line x equal 1. So what we need to think about is this height if I wanted to find an expression for it, I have to again use subtraction. And now let's think about how we would use subtraction if we have a horizontal distance. How did I find a horizontal distance in the previous example for the radius? I had to subtract two x values. How did I do that in the example before that? When I found the radius, I had to subtract two x values. So I have to do the same thing now with this example. The dot on the right in red, that has an x value of 1. What would be the x value for the dot on the left? Well, that has to relate to the curve. We saw an example like this in the previous section. If I'm given a curve in terms of y as a function of x, I can flip that around. So if y is equal to square root of x, that means the exact same thing as x is equal to y squared. We're noticing that this is a parabolic dish that's opening to the right, so it shouldn't be surprising that we can think of that as x as a function involving y squared. So x values on the left come from y squared, x values on the right come from 1. So our height would be the x value that's on the right, which is x equal 1, minus the x value that's on the left, which is x equal y squared. So in fact, if I'm subtracting those two x values, this just turns into 1 minus y squared. Notice we used right minus left to figure out the height. Okay, so now what about the radius? So the radius means where I took that little slice right there, and actually not really a slice, where I'm imagining my height is, and then I'm about to rotate that about my axis of rotation, that has a particular y value. So now how far is that y value from the axis of rotation? This would be my radius. Your radius is how far is this point from the axis of rotation. So this would be top minus bottom, which is the y value that's just equal to itself minus the y value that relates to the axis of rotation. The x-axis has equation y equals 0. So your radius is just y minus 0, which is y. This is actually exactly analogous to what we did in our first example. It's just that our axis has changed. So now we have our radius, and we also have our height. So now let's put all of this into our volume formula. So volume is equal to the integral from a to b of 2 pi times radius times height. And then we need our differential. And I'm just going to use the word differential here, because we want to think about what our differential has to be in terms of, and that's also going to help us with what are our a and b values in terms of. If our radius is in terms of y and our height is in terms of y, then our differential has to be dy, and then our limits of integration have to be y values. So notice the shape that we had also went from y equals 0 to y equal 1. So that becomes our limits of integration. Our radius we said was y. Our height we said was 1 minus y squared. And then our differential would be dy. And I just want to make a note just to remind you, this top limit is really y equal to 1, and the bottom limit is y equal to 0. I know coincidentally that's the same as the x values that we were given, but it's important to keep that in mind. I took that from the limits relative to y. So now let's just integrate as we saw in the first example. I'm going to factor out the 2 pi. I'm going to distribute the y so that I would have y times 1, which is y, minus y times y squared, which is y cubed. And I'm integrating with respect to y. This leaves me with 2 pi times my antiderivatives, y squared over 2 minus y to the 4th over 4, evaluating at 1 first and then 0. Plugging in 1, I get 1 over 2 minus 1 over 4. And then plugging in 0, I would get 0 minus 0. Again, I encourage you to follow through on plugging in your limits of integration. Some of the problems you're going to see for these sections are purposely giving you simple limits of integration so that you focus on the setup and the antiderivatives. But don't always assume that you're always going to be plugging in 0 at the end. So then this is just leaving me with 2 pi times 1/2 minus 1/4, which is 1/4. So I end up with pi over 2.